This study is part of an ongoing research project devoted to the exploration of the acoustic activity that is generated in brittle building materials when they are loaded mechanically. The motive of this part of the project is to detect signals that could be potentially pre-failure indicators, and in this study we take advantage of the evolution of the cumulative counts of the acoustic hits. The novelty of the study is related to the parameter that is chosen in order to study the acoustic activity. We have decided to use the cumulative counts of the acoustic hits, which is a rather disregarded parameter. However, sometimes it is advantageous because it eliminates uncertainties arising from improper setting of the acoustic emission timing parameters. The second novel aspect of this study is that the analysis of the data is implemented in the natural time domain rather than in that of the conventional time. We can see here a short overview of the presentation. We discuss a few words about the natural time concept, and then we'll present the experimental protocol. Then we'll proceed to the analysis of the experimental data, and we will compare the findings of the present analysis with the respective ones of analysis based on well-established approaches. Concerning the concept of natural time, it was introduced by Professor Varotsos and his team after many years devoted to the study of series of experimental data. It has been proven that if we analyze experimental data about the acoustic activity or electric activity in terms of natural time, this isn't advantageous because we extract the maximum possible information during the study of complex dynamical systems, and the analysis in terms of natural time provides data about the instant at which the system enters into its critical stage. It is mentioned that originally the concept was developed for the field of seismology. Gradually it became a very interesting and valuable tool for the study of natural events leading to disastrous phenomena. Today, natural time is applied in a very broad variety of scientific disciplines, including some fields that are shown indicatively here: mechanics of materials, medicine, physics, engineering, structural health monitoring, etc. The main characteristic of the analysis of a series of acoustic events in natural time is that if we have a series of acoustic events that in the conventional time are unequally spaced, as it is expected, we have a dense distribution of events as we approach to the instant of fracture, for example. If we use the natural time, then the same events are equally spaced along a new parameter, which is characterized, denoted as natural time. And in this way, we keep only the order of appearance of the event, ignoring the exact conventional time that it appeared. For example, let us assume that while loading a brittle specimen, we recorded n acoustic hits. Then we have a time series of cumulative counts, which is shown in this line here. T1, T2, Tk denotes the instant at which each hit was recorded. Now, we assume further that the elements of the above time series are normalized over their maximum value, which is obviously the value recorded at the instant Tn. Then we build a new time series, you can see in the second line here, where the term Cc star is equal to the cumulative counts corresponding to the time instant Tk divided by the cumulative counts recorded at the end of the experiment. This series in the natural time domain is translated to a new one shown in the third line, where the parameter Hk denotes the temporal order of appearance of the kth event. In other words, Hk is equal to K over N. The above described procedure is clearer shown in these two plots. We consider an arbitrary experiment during which we recorded n acoustic hits, and we focus attention on a window with 10 successive hits in an arbitrary time interval from the 45th to the 47th second. We have plotted both the load and the cumulative counts in the left figure in terms of the conventional time and in the right figure in terms of the natural time. As it can be seen, in the right figure we have an even distribution of the values of the cumulative counts along the parameter of the natural time x. The evolution of the cumulative counts in this study will be implemented in terms of the so-called M function, which reflects the slope of the linear trend line of a number of n successive pairs of cumulative counts and natural time. In fact, we divide the overall number of hits recorded into k groups, and then we simulate each group by a trend line of linear nature, and we calculate the slope of this trend line in terms of the x parameter, in terms of natural time. Then we proceed to the second group, to the third group, and so on. In this way we obtain k values for the slope m, and we can plot these values in terms of the parameter x, in terms of the natural time, to obtain the evolution of the slope of the cumulative counts in the natural time domain as it is seen in this figure here. Usually the procedure we described in previous slide is called sliding windows procedure, and it is schematically shown here. We assumed that we have a time series with 25 events, and we considered groups of 10 events each. For each one of these groups, we calculate the slope and the average natural time instant. Then we move to the second group, which includes, let us say, from the 6th to the 15th, 10 elements again. We calculate the second value for the slope and for the average time instant, and so on. So in this way we obtain pairs of the slope and the respective average value of the natural time. The data that were analyzed in this study were obtained from an experimental protocol during which marble prisms were loaded under uniaxial compression. During this protocol, we used 4 loading rates in order to study, in addition, the potential role of the velocity of the speed of loading. During each experiment, we recorded the load that was applied, the axial strain that was developed, and also the acoustic activity by means of 6 RA sensors. We can see here some characteristic raw data. The first figure corresponds to the axial stress-axial strain plot. It is characteristically that the specific variety of marble exhibits an almost perfectly linear response, and only during the very last loading steps the response becomes non-linear. In addition, you can see in the second figure here the acoustic activity, and it is critical to emphasize at this instant that the acoustic activity is strongly intensified only during the very last seconds of the experiment. Proceeding to the analysis of the experimental data, we decided to present here the data corresponding to the lower loading rate, which was equal to 34 kilopascal per second. As it will be seen, the results for the remaining loading rates are almost identical from a qualitative point of view. In the first plot, we can see the normalized cumulative counts in terms of the conventional time. It is clear that the acoustic activity is strongly intensified only during the very last loading stages. During the initial stages of the experiment, the specimen is almost silent. If we apply the procedure mentioned and we translate this time series of cumulative counts in the natural time domain, we obtain a completely different view concerning both the development, the evolution of the load, and also the evolution of the cumulative counts. If we calculate, according to the sliding procedure, the values of parameter m, of the slope of the subgroups of the time series of acoustic events, we obtain the lowest figure here. And what is very important to emphasize is that the evolution of the slope at an instant at which the load approaches its maximum value obtains the value m is equals 1. The evolution of the function m for the remaining 3 loading rates is shown in this slide, and as I have already mentioned, it is clear that from a qualitative point of view, the response, the evolution of the parameter m is almost identical. There is a clear plateau at which the parameter m obtains the value m equals 1. A synopsis of the numerical data for all 4 loading rates is shown in the table of this slide. The main conclusion that can be drawn is that independently of the loading rate, the function m exhibits a very clearly distinguishing plateau as the applied load tends to attain its peak value. This characteristic plateau appears systematically at about the central natural time instant, and the value of the respective parameter is equal to 1. The duration of the plateau indeed does depend on the loading rate, and the same is true for the distance of the end point of this plateau from the fracture instant. The dependence of the extent of this characteristic plateau that is exhibited by function m in terms of the level of the applied load is shown clearly in this figure, and it is almost linear. The dependence of the duration of the plateau of m on the loading rate is shown in the left figure here, and also in this figure we can see the dependence of the duration of the stage with m higher than 1 also on the loading rate. In the right figure we can see the dependence on the loading rate of the percentage duration of the 2 stages, namely the stage with m equals 1 and m higher than 1. As a next step, the same data that were analyzed in terms of the m function are now analyzed in terms of additional parameters, and as a first one we decided to use the f function, which reflects the average frequency of generation of acoustic hits. Further details about the application of the specific technique for the analysis of experimental data can be found in these 2 publications. It is convenient to plot the values of the function along the time to failure parameter instead of the conventional time, and you can see in this figure a typical plot of the acoustic activity in terms of the f function, and also in the same plot you can see the evolution of the load that is applied. It has been proven that during the last loading steps the f function is governed by a power law, and it has been proven also that the onset of validity of this law is a safe pre-failure indicator. We have plotted in this slide, indicatively only, the evolution of the f function for the experiment with the highest loading rate. And then we have plotted in the right figure, comparatively, the evolution of the m function, and in juxtaposition we have plotted the evolution of the m function. It is very interesting to observe that while the f function is governed by the power law, the value of the m parameter is almost constantly equal to 1. Another parameter of the acoustic activity that is proven that it provides very interesting results concerning the proximity of the loaded system to the fracture instant is the distance between two successive acoustic events, which can be determined if we use a number of acoustic sensors instead of a single one. In order to plot this parameter in terms of time, we use again the sliding window procedure. We divide the number of events into k groups, and for each group we determine the average value of the distance between the sources of all the members of the specific subgroup. Then we pair this value to the average time instant during which each one of the events of the subgroup were determined, and so we obtain pairs of the distance, the average distance, and the average time instant, which corresponds to this average value of the distance between the events. A characteristic plot of the evolution of the distance between the acoustic sources during a typical direct tension test is shown in this figure in terms of the time to failure. You can see that originally the distance between the sources is equal, let us say, to about 8 seconds, and gradually, as the load approaches its maximum value, the distance between the sources decreases and finally it obtains a minimum. Slightly before the fracture of the specimen, the distance between the sources starts increasing again. It is considered that the instant at which the distance between the sources obtains its minimum value is a typical and very interesting pre-failure indicator. The results for the present protocol, the protocol discussed here, are shown in this figure. Again, the distance between the sources is relatively high, equal to about 40 millimeters, and as the load tends to approach its critical value, we obtain a minimum value of the distance between the sources, which starts increasing again. As we have already mentioned, this study is part of a wider project that is already in progress. As a next step in this project, we have proceeded to the study of specimens made of reinforced concrete, which are under 3-point bending. Some preliminary results of this next step are shown in this figure here. It is again concluded that as the load tends to approach its maximum value, the parameter m, the slope of the cumulative counts in the natural time, attains a value equal to 1. The main conclusions of this study are summarized in this slide. The most critical one is the existence of a clear plateau that is exhibited by the cumulative counts if their evolution is studied in the natural time domain. The onset of this plateau is believed that provides us with a very interesting index that warns us about impending entrance of the loaded system into a critical stage. There is a very good agreement between this specific pre-failure index and the respective indices that are provided both by the function and also by the evolution of the distances between the acoustic hits of the specific protocol, at least. Finally, it should be mentioned that the next steps of the protocol, of the project, provide data that are also in very good agreement with the results obtained from the study that we discussed in this presentation. I would like to thank you very much for your kind attention.